Okay, so this is lecture 22 of our VLSI device course. So sorry for this late start of my lecture. But I already announced it to my enrolled students. So due to my personal issue, so I was not able to start on time. So instead, I started a little bit early, a little bit late. Okay, so now let's go to this lecture 22. So in the previous lecture, we have considered the strong inversion case, and we have found that, okay, so when we have very slight difference in our surface potential, so starting from just 0.85 and 0.88, so the distance is just 0.03 uh, volt. However, it is corresponding to significant change of our um, electron density. So compared with this amount of electron density, then certainly we have a much higher electron density. And also the shape of our electron density shows rapid decrease from the surface into the substrate. So according to our current approximation or expression, so electron density shows exactly the peak value at the interface. However, at the end of our previous lecture, I told you that actually we have a slight distance from this exact point, because in this case here we have a silicon, and this is corresponding to silicon dioxide, and from the viewpoint of our silicon electrons in the silicon, this silicon dioxide is regarded as a very uh, high barrier. So barrier height is just 3.1 electron volt. So actually this x equal to 0 point is corresponding to the boundary attached to the high barrier. So it has a lower probability to have electrons. So it means that we cannot have actually many electrons at this point. So it is slightly moved from this one. So what is the actual consequence of this slight movement of electronic peak from exact surface into the a little bit substrate? So that is corresponding to change of effective capacitance. Please have a look at this calculation result. Yes, this curve is corresponding to our current approximation. Okay, if we follow our current consideration without considering the location of electron peak, then we will have this quantity. Okay, so once we have sufficiently high gate voltage, then after that our electron density, so electron density, inversion charge density, just linearly increase, and this slope is corresponding to actually oxide capacitance given by oxide permittivity divided by oxide thickness. So this is the actual physical thickness of oxide. However, when we consider such kind of effect, quantum confinement effect, peak distribution is a little bit away from the surface. So means that from the viewpoint of our gate, if we consider just this semi-classical description, then electrons are found just away by amount of T ox. However, if we consider this quantum confinement effect, then from this gate terminal, now our electrons are located somewhere even further. So this is kind of a 10 or 20 Armstrong, which is extremely short. However, this difference can really make such kind of huge differences in their inversion charge behavior. So maybe you can find that, oh, so what is the difference between these two lead graphs? So this one solid filled circle considers the quantum confinement effect, and this one is without quantum confinement effect. So in this case, effective distance is longer than semi-classical one. So also we can say that effective thickness is enlarged. So it is corresponding to the reduction of effective capacitance. That's the reason why we have slightly degraded slope in this case of blue and red ones corresponding to different devices. So this is universal for every cases. Okay, so that was just remaining story of our previous lecture. And now we have tried to express our silicon charge as a function of surface potential. So we were able to derive this relation. So what was the result? The result is that, okay, if we have surface potential, then for this planar MOSFET case, we can find even an analytic expression. Although it contains a lot of terms, exponential, linear, again exponential, but anyway, that is just a given function. So once we have surface potential, then we can automatically calculate the silicon charge. So, however, now think about this one. Here, when we have a MOS structure, so now we are saying that if we have a certain surface potential, then from this one, we can now understand the amount of charge collected at the surface. Okay, great. But can we change this surface potential directly? For example, can we attach a certain contact into this surface? Actually not. What we can do is just change the voltage of this metal part or substrate, but substrate is regarded as a voltage reference, so this is grounded, and we change the voltage applied to the gate terminal. So VG is controlled. So by changing this VG, then we can again change this surface potential, and as a result we can control this silicon charge, and this silicon charge of course contains inversion charge and depletion charge, and this inversion charge is used as our charge carriers. That is overall situation. So now we can control only VG, so we have to find out is eventually the QS not a function of phi s, but QS as a function of gate voltage. So how can you do that? So we can apply this MOS equation. So simply speaking, it was given as the additional voltage beyond this flat band voltage is divided into two parts. One is oxide and one is silicon. Yes, the silicon part is given here. And now we observe this important step. So since we have here oxide layer, and the difference, voltage difference across this V ox can be well represented as this one. Minus times Qs is corresponding to C ox times V ox. Why we have this relation? Because this is the oxide is just a simple dielectric material, and here we have a relatively negative charge and relatively positive charge, so minus sign comes from that way, and the voltage difference C times V gives us our charge. So simply we can easily identify this relation. So now let's convert it to another form. Vx is simply given by Qs divided by oxide 1. So now you can see that this form, and please note that this Qs has a functional form dependent on the Qs. So this equation, Tower equation 2.195, can be regarded as an equation for surface potential when gate voltage is given, and of course from its construction, flap end voltage is also given, and Cox is given. Then we can solve this non-linear equation to eventually get what? Get phi sub s. So now that was our purpose. When given value of when we know the value of gate voltage, then now by solving this tower equation 2.195, we can calculate surface potential. Of course, when we know surface potential, as I told you before, we can calculate Q sub S, and that's it. So we can solve the above equation. And we have homework number 5, although I do not check the homework then, but I strongly recommend you to this homework by yourself. Okay, now please draw your surface potential as a function of a gate voltage. Maybe you may assume that gate voltage is positive because that is our usual operation case. Then please assume these numbers, yes, 10 to the 17 per cubic centimeter for acceptor density, and oxide thickness is 10 nanometer. Oh, that is quite thick, so quite old technology, and flap end voltage of minus 0.88. Okay, anyway, using this number, then please draw your phi s as a function of Vg. So please try to that. Then how can you calculate this one? So although here independent variable is Vg, but in my opinion, it is much easier to use it this way. Just to fix a value of phi s, then you can calculate Vg immediately. So how can you do that? Once again, of course, this equation can be regarded as an equation for phi sub s. However, on the other hand, if we have phi sub s, then it becomes just an expression for v sub g. So following that manner, please change your values for phi sub s, then you can calculate the corresponding value for Vg, then you can draw it. Please check your result. Okay, so now let's go to, now also about that. This is a MOSFET. So did I make the same mistakes? Okay, here only one. Okay, now we go to the chapter now 3 of tower. Okay, let's go. However, before starting our analytic expression, then just to have a look at our result taken from TCAD simulation. So here we have a device having a quite long length. Channel length is 1 micrometer. What is 1 micrometer? It means that starting from this source side and ending at this drain side, this length scale is given as 1 micrometer. Okay, so current technology, 1 micrometer can be regarded as quite a long channel. because nowadays we can make much shorter channel. But if you have older technology, then maybe 1 micrometer can be a short length. So whether a certain length is long or short really depends on technology. So if you are working with quite much scaled technology, then 1 micrometer can be regarded as a quite a long channel. So in this case, its technology node is roughly 90 nanometer technology. Means that you can draw your length, data length around 90 nanometer, not exactly 90 nanometer, but or around that number. So it means that this 1 micrometer is at least more than 10 times longer than minimum available length scale, so it can be safely regarded as a quite long channel device. And here we have a certain flat band band voltage, and please have a look at this one. Here we have oxide thickness and 1.2 nanometer. So how did I understand this is or estimated this is 90 nanometer technology? Because this oxide thickness is effective oxide thickness is 1.2 nanometer. This is a certain indicator of length, uh, technology node. Oh, how can we understand this relation between oxide thickness and technology node? Usually, technology node is characterized as the minimum gate length we can have. However, also when we have a shorter device, then of course the TOX is also scaled. So if we have a thicker oxide, then that is corresponding to the minimum length much longer than advanced one. So 1.2 nanometer, historically 1.2 nanometer thick oxide thickness was for 90 nanometer technology. And from this quantity, of course, we can calculate this COX taken from epsilon ox divided by CT ox. Please note that this C ox usually called as oxide capacitance. However, this is not exactly capacitance. If this is really the capacitance only, then we will have the unit of farad. However, as you can see here, this is just given by farad per square centimeter. So this is area component. So if we have a wider area, then we will have eventually larger capacitance. So per area, a capacitance is given as COX. Okay, please note this dimensionality. And BDD is in this simulation, it was given as 1.1 volt, and typically 90 nanometer technology, the BDD was 1.2 volt, but I don't think that that makes much difference in our calculation. So anyway, we will consider this a typical example of a 90 nanometer technology. And when was it used? It was used early 2000, so more than 20 years ago, this technology was used. Oh, then that is quite old technology, but please understand. So this is good for our educational purpose. Then let's go to our simulation result. So this simulation result first shows input characteristics. When we say input characteristics, it means that we change the input variable. Then what is the input of our transistor? Our transistor has, yes, gate voltage as its input voltage. So we change VGS and observe the output variable, that is ID. So although we say input characteristics, we are not observing, for example, IEG. Eventually, we don't have this quantity at this case because we consider quite a good oxide, um, gate oxide. This is a good insulator. So we consider ID versus VG characteristics, and that relation is written as input characteristics. Here we have VGS, and here we have ID, and this is the first graph we must draw when we characterize our MOSFET. So you can see that here we have two different curves. What is the difference? Here we have two different VDS value. So in this case, we have a relatively small number, quite close to 0. And this number, 1.1, is, yes, that is the maximum voltage we can apply in this technology, VDD. So, simply speaking, when we draw this input characteristics, typically we draw two curves. One is a small VDD or low VDD value, and one is, sorry about that, a small or low VDS value, and another one is VDS equal to VDD. So in these two cases it should be drawn, and simply speaking, this curve, yes, this curve gives us just what is the on and off characteristics of this transistor. So since now we have quite a small and low value of VDS, so transport, the movement of our electrons are quite slow. So this is just showing the properties of mainly the number of electrons. How many electrons are there that represented by this behavior? So please have a look at this curve. Then you can see that, okay, below certain voltage, then we have almost no electron. After that, now we have a certain electron and it is linearly increasing. So that is shown here. Of course, in the contrast to our real electron density or electron charge versus VGS relation, here we have a little degradation. So this is not exactly linear, and its slope is continuously reducing. So it is because this quantity is not only a function of Qi, inversion charge density, but also a function of our effective mobility. Mobility is also play a certain role in this graph, but anyway, the overall shape is determined. The large variation is this on-off characteristic is determined by this more severely varying this Qi, and another slight modification is related with this effective mobility. Okay, the left-hand side, we are now looking at a curve corresponding to input characteristics, but at the same time, we must draw this right side one too at the same time. I mean that which one is more frequently used? So there is nothing like that. We must draw both of them. And this one shows the same linear gate voltage. However, the same quantity is just drawn in the semi-logarithmic scale. So now here we have 10 to the minus 5, 10 to the minus 6. Yes, each tick shows a decade changing. So in this case, now you can see in this part, oh, so even below certain gate voltage, so we feel that in this gate voltage lower than certain value, threshold voltage, then maybe the current conduction is not allowed because we don't have enough electron density. Yes, we don't have enough electron density, but we have electron there. So this small amount of electron actually conduct small amount of current. So this current is called as sub-threshold current because our voltage condition is lower than threshold voltage, so we call it as a sub-threshold current. Okay, beyond that, okay, now we have certain current conduction, and this almost linear curve is now written as this form. Yes, also it shows a certain behavior, and it is also written as or drawn as this behavior. So details of these curves are not clearly visible in this semi-logarithmic graph, but it is true that it is increasing monotonically when we have higher and higher gate voltage. Okay, then certainly since we have a higher VDS, so VDD, so in this case we have more current conduction. That's true because here we have a source and drain, and now we apply even higher voltage. Yes, then there will be more current conduction. That is quite reasonable and understandable. So this is there exist differences. And one interesting point is if we go to subthreshold current, actually the difference seems to be quite small, actually almost no difference. We will revisit this one later. But anyway, this semi-logarithmic curve gives us important findings. Okay, what is the sub-threshold value and the behavior of this curve, and especially this number is important. So what is this? This is the current obtained when gate voltage is equal to VDD. At the same time, also drain voltage equal to VDD. So both of our input terminal and output terminal are biased with the maximum available voltage. So this is corresponding to the maximum current this device transistor can conduct. So usually this current is written as on current, and we wanted to understand the value of this on current. If this on current is high enough, then we uh, call a certain device as a high performance device. Performance here means that the value of on current. And another important quantity we can find is this one. Can you see it clearly? So let me use a different color here. And this is corresponding to the case where gate voltage equal to 0 at the same time drain voltage equal to VDD. It means that although we apply zero gate voltage, so we wanted to shut down this device. However, by action of this high drain voltage equal to VDD, we have unwanted current. So this value is our wanted current, and this current is our unwanted current. So our aim is to reduce this unwanted current, usually called as I off. At the same time, we wanted to maximize this wanted current I on. Yes, that is our usual aim to fabricate this device. Well, anyway, let's move on to our next topic. So because we have many things to cover. Okay, that was the input characteristics, but uh, we must also consider output characteristics. In this case, oh, sorry about that. I have a typo here, VGS. Then I have to also change this one, VDS. Now, when a gate voltage is fixed, then we can change this VDS values. So since this VDS, drain voltage, is regarded as output voltage, so this characteristic, this curve is also frequently referred to the output characteristics. This is the typical curve, and when we have higher drain voltage, then first drain current is increasing, or because we now apply even higher and higher voltages, so electrons are more and more accelerated, faster and faster accelerated. So it is true that we have accelerated electron. That's the reason why we have an increasing current. However, uh, when we apply too high voltage, then in contrast to our naive expectation, so increasing and ever increasing, but eventually this current is now saturated and no longer grow. So usually our own current is corresponding to this rhythm. So please have a look at this curve. Where can you find this on current? On current means that we apply VDD both to gate terminal and drain terminal. And for drain terminal, we apply this one. And gate terminal, this is its topmost curve is corresponding to our VDD case. So this point is corresponding to our own current. Certainly, this own current is saturated and nothing related with this, this linearly increasing curve. Okay, then if I ask you this question, how can you answer? Where can you find the off current? Yes, off current is exactly zero in this graph, because this is just a linear graph. And now here we have gate voltage of 0 0.6, 0 0.5, 0 0.4, 0 0.3. Even when we have gate voltage equal to 0 0.3, we have quite a low current. But if we go to 0 0.2, then it is certain that we have just a horizontal line exactly matches to y equal to 0 curve. So now we don't have any current meaningful curve in this linear scale. Of course, if we draw it in linear scale, then we will have a value corresponding to a certain number, but in this linear curve, we do not see any meaningful number. So now you can understand there exist two different modes, triode mode and saturation mode. And in this graph, the curves corresponding to this part or that part or this part, these are corresponding to our saturation mode. In this case, our drain current is no longer dependent on the drain voltage, so we have a certain value almost fixed. I mean that here our drain voltage in general, it can be a function of gate voltage at the same time drain voltage, but in this saturation mode, actually this drain current is only a function of gate voltage when we have a sufficiently high drain voltage. On the other hand, in the case of triode mode, of course, our drain current dependent both on gate voltage and drain voltage. Yes, that's clear. Okay, so then now I think that I have explained sufficiently about long channel simulation result, but this is just a simulation, and the main part of our course, the main difference of our course, entire course, uh, uh, against our junior level course is shown here. So from now on, we will consider very important lesson of this course. Okay, so think about our derivation for current, drain, MOSFET drain current in your microelectronics course or your junior level course. It contains a lot of certain ambiguity, but in this course we are now trying to derive the current expression as accurate as possible or as rigorous as possible. So let me just show you how can we do that analytically. Of course, the most accurate way would be just to use our ticket simulation. However, this textbook just to show how can we further mm, expand our formulation, analytic formulation as much as possible. That will be quite useful for us to deeply understand the operation of this device. So this is quite important in my opinion. So typically in such kind of thing, we introduce this schematic coordinate system, and x is regarded as a vertical one. Why we have x equal corresponding to vertical one, not channel direction, because previously we just consider M O S system and we just use X for that depth direction. So we just keep the coordinate system. So X equal to 0 is regarded as the interface between our silicon material, as shown here, and oxide. So if we go to positive infinity, yes, there will be deep substrate. And if we go to x equal to minus t ox, and then we will have the end of our oxide, and now metal starts. So beyond this point, we have just metal. And here we have oxide here, and it has a length, the gate oxide has the length of L, capital L, so it is corresponding to y-axis. Of course, x, y, z, but this z direction is just regarded as the least important one because we assume the homogeneity or uniformity along this z direction. So it is just treated as treated with the multiplication factor W. So if we have twice wider transistor than this drone device, then we have such kind of schematic, and all quantities, current quantities will be just multiplied twice. Yes, 2W will be multiplied to our current. Okay, so the g direction is not that important. So when we have a certain for example Poisson equation, we consider only x directional and y directional partial derivative, then does not consider the g directional partial derivative. Why we don't have this one? Of course, in principle we must consider this one. However, in this case we assume the uniformity along g direction, so we can neglect this third direction. Okay, I have covered this x equal to silicon substrate, and 0 and L is corresponding to the source end. This is a source, and here we have now source, and here now we have drain. And Source and substrate are grounded in our approach. Yes, this is grounded, and also here we have grounded substrate, and um, quite typically we assume uniform p-type substrate. Here we have Na acceptor density. Yes, that is the setting we will continue. Okay. Then our aim is, of course, to calculate the drain current. Yes, we have already seen the drain current, but it was obtained by complicated TCAD simulation. We wanted to have some way to calculate with our hand calculator. With the hand calculator, can we calculate certain values? So that is the main aim of our today's talk. But I think I don't expect that we can finish it within a short time. But anyway, let's do it together. So first we start from gradual channel approximation. So what is it? So this approximation assumes that the variation of the electric field in the y direction. What is it? So what is the electric field in y direction? Of course, this is given by, so this way. This is y directional electric field, but I'm not talking about the y directional electric field itself, but instead of that, this gradual channel approximation states that variation of electric field in the y direction. It means that instead of this first derivative, now we consider its once again derivative with respect to y. So second derivative is considered is much less than corresponding variation in the x direction. Means that we can also consider x directional, vertical directional electric field, vertical directional electric field, and its variation is given as, yes, this one. So compared with the second derivative with respect to x, so second derivative with respect to y, the channel direction, horizontal direction in our drawing is much, much smaller. That is our approximation. This is the gradual channel approximation. Why we have to introduce this approximation? So in our original Poisson equation, we must consider this form. Here we have second derivative with respect to x and second derivative with respect to y. Of course, we must consider the d-directional one, but as I told you before, due to the uniformity assumed, that doesn't appear here. Yes, now we have a Poisson equation containing two different directional second derivative. However, if we adopt this gradual channel approximation, things becomes amazingly simple. What? This term is completely neglected. So now we can once again only have an equation only having x directional derivative. Of course, here we have y-axis coordinate again, but please note that there is no derivative with respect to y. So y can be regarded as just a given number, and only x can be regarded as variation or independent variable. And we were able to get certain information for that one-dimensional system already. So we will try to utilize that information as much as possible, even for this two-dimensional structure. That's the point. So simply speaking, when we have this x and y direction, our Poisson equation should consider two different directions simultaneously, but by applying this gradual channel approximation, then we just make our analysis once again additional. So this two-dimensional system now just a collection of several one-dimensional systems. So that is the great simplification we can achieve from this gradual channel approximations. Of course, you can ask me the validity of graduate channel approximation. So of course, it is not applicable to every case, but in many cases, we can use this one. Okay, so another one we will consider in this course as a more advanced course is now we consider electron quasi-Fermi potential. Please note that electron quasi-Fermi potential was written as phi n in our previous notation, but here following our textbook notation, we introduce this V of y. Please note that this is nothing but just electron quasi-Fermi potential. Well, however, here we have a really important meaning for this expression. V or phi n in general should be written as x and y. Of course, this is a two-dimensional space, so we must consider this a two-dimensional quantity. However, please have a look at this line. It is assumed that V, electron quasi-Fermi potential, is independent of x, not y, but x. Vertical direction, V is independent. It means that when we draw our MOSFET in this way, so along this direction, x direction, quasi-Fermi potential is almost constant. How can it justify this approximation? So why? From our intuition or many understanding, now we understand in this MOS structure having source and drain, then electrons are moving in this horizontal direction. So current density is predominantly y directional. So it isn't moving in this way and it does not move in vertical direction. It means that since electron current is just proportional to the gradient of electron quasi-Fermi potential, so if we have variation along this x direction, for example, if we have certain values v and if we have a different value v prime, then there will be a difference and there will be the vertical current conduction. But it is not observed in reality. So the reason is because they share the same electron quasi-Fermi potential. Yes. So due to the observation of a predominance of a y-directional current conduction, we have no x-directional variation of quasi-Fermi potential. So quasi-Fermi potential varies mainly along the y direction. That is our important observation. So maybe you can find that the original very complicated problem becomes simplified further and further. For example, our Poisson equation should be two-dimensional, but now we have only one-dimensional Poisson equation. And actually, our electron quasi-Fermi potential can be two-dimensional quantity, but now we consider only this one-dimensional variation. So it means that at a given slab here, then we have only one Poisson equation and fixed electron quasi-Fermi potential. So once electron quasi-Fermi potential is fixed, then we can also have just simple proportionality between exponential of potential and electron density. We will use this information in our derivation. Yes, as shown here, electron density is just proportional to electrostatic potential. Of course, here we have offset, and this offset is given as electron quadriform potential. Please note that now, when we consider certain Poisson equation, we can treat this y as x and y, and this y value is given. And in this case, v is only function of y. Since y value is given, this v is just a constant. Wow! So we have quite a similar expression for electron density, just like 1D problem. Only difference is our electron density is now modulated by this additional electron quadriform potential. That is the key difference. So I highlighted here with red color. Then now we can recover many of our previous expressions. So please note that we are now talking about electron quadriform potential. In the case of hole density is not given by electron quadriform potential. It is given by the hole quadriform potential, but in this system, our substrate is just grounded. It means that in entire our system, okay, we can also consider hole density, hole quadriform potential is just 0. Because this contact is p-type, this material is p-type material, and this is p-type contact, so this one directly affects on entire p-type region. So we can say that hole density is just looks exactly same as before. So when we write down the expression for electric field, for example, this expression contains the result of hole density and electron density and doping density. Among various terms, only the terms related with electron density should be modified with exponential minus quadriform potential normalized by our summer voltage. That is shown here. This is the modulation, and this modulation modification just occurs in front of electron related terms. So all other parts are just remained as the same as before. So for example, this one is corresponding to what? This is related to hole density, yes, and this is nothing related to neither electron density or hole density. This is corresponding to just doping density. Okay, and this term is related to doping density. So simply speaking, even in this two-dimensional system called as MOSFET, not in this MOS capacitor, but MOSFET FET, but in expression for vertical electric field. So please note that this is a vertical electric field, and this is just a modified version of our MOSFET expression. It means that, yes, so if we have positive electrostatic potential, and of course this red colored one will give us even smaller value than number 1, positive number, and here we have a minus sign, and this one gives a small number. Please note that this value, in the coefficient itself is already quite small, and our electrostatic potential should overcome that small coefficient to get surface inversion. But now when we have a certain positive gate potential, also that uh, when you have a positive electron quadriform potential at a certain point, a certain x point, then our surface bending should be even higher to get the same amount of surface inversion. That should be compensated. So now you can understand the condition for surface inversion is now changed from its previous value. Previously, it was sufficient to just bend our conduction band 2 times phi b, but now we have to consider additional v because our offset is given as minus v. So that should be first cancelled by this amount of voltage, then band bending. After that, we must apply another 2 times phi b band bending. So also, simply speaking, now we have to consider even enlarge the maximum depletion width because we now have wider surface potential. So now we have this one. Yes, previously we just had this one. In the case of a MOSFET, we can consider this is equal to 0, and that was the previous expression for maximum depletion width, but now we additionally have the position dependent quantity. So please note that when we have a MOSFET, then here and there we can have a different electro quadriform potential. For example, the boundary condition at this source side is just 0. And boundary condition at this drain side is given as drain to source voltage difference because simply the electron quadriform potential follows at terminals follow the applied voltage. So this applied voltage is 0 and this applied voltage is drain voltage, and since the source is grounded, so this is corresponding to VDS. Okay, so let me make a quick summary. So with the gradual channel, oh, sorry about that, I made another mistake, gradual channel approximation. So I will fix all of my typos. When we have gradual channel approximation, our MOS expressions previously studied in our previous lectures can be reused only with modification by amount of V, especially the terms for electrons. So that was our simple understanding. Okay, so we are now ready to study the drain current. Okay, so of course, drain current can contain also some contribution from electron current, and contribution from hole current, even contribution from displacement current. However, this component is not important when we consider steady state. Yes, we can certainly neglect this one. And this is hole current. However, when we consider the atmosphere, we can also neglect this hole current. So now we will consider only electronic current because that is the most important and major contribution to our current. Yes, this is not that much problem. And now when we have a look at this one, this expression, the current density at a certain position can be simply written by this expression. What is it? This is nothing but just a directional component of our previous expression shown here. Yes, so that is not that difficult. Of course, in general, this gradient should have x directional and y directional gradient, but we have already assumed that this electron quasi-forming potential varies only along y direction. So now instead of this x and y directional uh, variation, we can only consider this y directional variation. That is quite reasonable. Yes, and please note that also this expression already contains both of drift current and diffusion current in it. Okay, this is quite easy to understand. So now think about this one. Here we have certain structure, and every point, yes, we can define at every point inside our system, we can define Jn. Yes, this Jn is heading y direction. So by our assumption, so they are heading this direction. Then what is the current? This is current density, and in order to obtain current, we have to make an integration along this vertical direction. So as I told you before, this current is obtained by integrating this current density over x point. Well, actually, I have to be more accurate. Actually, we must make an integration over a cross section. So we must do two-dimensional integration. However, fortunately, so this g-directional integration is just done by multiplying this w. So, okay, so this g-directional integration is already covered. So now the remaining integration is only for x direction. So starting from 0 point, x equal to 0, and we go to this vertical direction and stop at certain point. Okay, so what is x sub I? So of course, our electrons will just located here, just nearby the x equal to 0. So the selection of xi is not that important. If we say x sub I is quite far away from the surface, or just several hundred or several nanometer away from that one. Of course, if we take it too short, then that makes a problem. But once our xi, for example, let me just show you an example. If our xi is in certain case larger than, for example, if our x I is, for example, larger than, for example, 100 angstrom. So it means that 10 nanometer or even longer. Then actually we have almost no electron in this part. So we can safely say that whether we set xi equal to 10 nanometer, 15 nanometer, 20 nanometer, that doesn't make a big difference for our integration. So therefore, we can quite safe to say xi equal to sufficiently long. Yes, sufficiently large value of x sub I is required, but at as much as we are beyond this thickness of our inversion layer, then it's okay. So after that, we don't care about exact value of x sub I. Okay, this expression nothing but just integration of our Jn over cross section. This cross section is W wide and Xi wide, and this X wide vertical direction integration is done here, and W wide integration is simply represented by this multiplying W. Okay, good. So now we can calculate the current at any position y. So we can calculate this y position. We can calculate ID. Also, this position, we can calculate ID. Everywhere starting from y equal to and ending at y equal L, select any value. Then you can have ID. But if they are different, then that makes some problem. For example, let's say that here you have some current corresponding to 1 milliamp, and in this point you have 2 milliamp. Then what is the problem? In this case, we don't have any current continuity in this box. From the right side, we have the incoming current of 2 milliamp, and yes, the left side we have outgoing current of 1 milliamp. It means that when we make a directional sum of this incoming and outgoing currents, then we don't have sum of 0. So it means that our situation disobey the Kirchhoff's current law in microscale, in this small scale. Actually, we can exactly derive this continuity of our current density, or more exactly the integrated current, so everywhere. So simply speaking, I want to say ID, although it is written as a function of y, yes, it can calculate. However, when we evaluate this ID at every position, then we must have ID which is independent on y value. That is the thing we wanted to say. Yes, so now let's have a look at this integrand. Integrand contains three different terms. Yes, here we have mobility, electron density, and dV over dy, y-directional variation of our electron quasi-Fermi potential. However, since this integral is just along x direction, this is independent on x, so we can pull it out from this integration. So simply this integration can be pulled out. Yes, so here we have this quantity. Also, this mobility can be a function of a position. However, instead of that, we just introduce an effective mobility. So please let me just write down in this way. So it means that we are now assuming this one. Mu n can be a position dependent quantity, and also n is position dependent quantity, and we make this one-dimensional integration, but that is approximated as effective mobility in front of this integration. And now we consider electron density. So a certain average mobility value is assigned. Then of course you can ask me this question: how can you exactly obtain this effective mobility? So that is another question and another problem we will consider. For a while, just to regard this mu effective mobility as just granted, so we can anyhow find it. Then in this case we can pull out this one. Then the only remaining is, previously we must perform the integration of a quite complicated quantity, but now we have integration of a relatively simple quantity, just electron density. Wow, this is a huge uh, simplification. Of course, this can be possible because we have already made a certain assumption like v is not a function of x and only a function of y. That was the key. We can make such kind of simplification and also introduction of effective mobility. Okay, so once we adopt this one, then we can identify this number as inversion charge. What is it? Just the total number of electrons integrated vertically at a given position. Then how, given y position, what is the area charge originated from these electrons? So of course it will have the unit of coulomb per square centimeter. So this coulomb is comes from this one, and per cubic uh, per square centimeter comes from the integration of per cubic centimeter electron density. So we can have this clear result. Okay, so then now starting from this one, then now we can calculate so okay, so now we have equation 3.8, and now here we have dy. This dy can be of course sent to here, then dy times id times dy is shown here, and here we have vd. So of course v and y can be interchangeable. So instead of this y, we just write down this v. It's okay because there are one-to-one correspondence between y and v. So now we have quite a clear expression. The left hand side only we have y dependence, and right hand side we have only v dependence. V is once again electron quadriformic potential. Then we can just perform the integration from y equal to 0, also y equal to L, y equal to 0 to y equal to L. Then since this is just a number, a constant, so it just becomes multiplying the length L. And this L is of course normalized, so here we have L here. And please try integrate this right hand side, and the right hand side integration will give us just this remaining problem. So integration of our inversion charge density with respect to electron quadriformic potential starting from 0 to VDS. This form is particularly important. So once we can find a certain expression of Q sub I inversion charge density as a function of V electron quadriformic potential, then we can try to make this integration. Then how can you do that? So I will explain this one from lecture 23. So let's have a look at the further formulation in lecture 23. So please watch this recorded L22 before coming to the lecture 23rd on this Wednesday. Once again, sorry for my this delayed lecture 22, and see you this Wednesday. Thank you and bye.